To build an underwater structure, you'll need some interesting engineering. A large bridge over a river or bay has its foundation rooted underwater. It's even more complicated with undersea tunnels. Underwater construction is challenging. Engineers need to deal with water pressure and corrosion from salt water. There's also a problem of finding suitable materials. The most typical of them are concrete, steel, and acrylic glass. Concrete doesn't care about water currents and doesn't get damaged by salt water. Steel provides underwater constructions with a strong structure. And acrylic glass is tough, long-lasting, and resistant to sunlight. It's also transparent. That's why it's often used to make windows in underwater buildings. Anyway, when the water is shallow, it's not that hard to build something there. Constructors create a temporary foundation. Then, on top of it, they build several piers supporting the upper structure. But if the waters are deep, engineers have to use other methods. Depending on which one they choose, water is either extracted or diverted during the construction process. One such method involves using a set of large driven piles. Those are long, thin columns made mostly of steel, but their interior is partially hollow. With the help of a huge hammer, they get driven into the waterbed, like nails are driven into a piece of wood. After that, these steel columns get filled with concrete through a special tube. The concrete displaces the water that was in the pile before. Concrete has the ability to set even when it's surrounded by water. That's why driven piles eventually turn into a stable foundation for overwater and underwater constructions. Driven piles are a very cost-effective way of building something that has to be fixed in place. They prevent things from being moved by the water current. Another way to build underwater structures is cofferdams. They are built temporarily and allow workers to create a dry space for the construction. The water gets pumped out of this enclosure, and the cofferdam works like a dam. A completed cofferdam looks like a massive pit with high walls surrounded by water. Cofferdams are made of rocks, steel, and even dirt. These constructions can be built fast and removed even faster. But the process of putting up a cofferdam is complicated and challenging for engineers. They have to make sure the structure won't flood or collapse. The simplest way to build a cofferdam is to pile up loads of dirt. But in this case, workers usually have to somehow make the construction stronger. It helps to protect it from the damage caused by water. Once the cofferdam is ready, pumps extract the water from its interior. Sometimes it's too expensive to build a very deep and strong cofferdam. In this case, constructors use several powerful pumps that get rid of excess water when it seeps through the cofferdam walls. If a cofferdam starts to fail, this process is slow and, luckily, predictable. On the construction site, there are not only main but also backup pumps. In case of emergency, they can kick into overdrive. Then, the water is kept out for the time the personnel needs to evacuate. Cofferdams are most often used during the construction of dams and bridges. But when a large ship, like a modern cruise liner, needs to be repaired, engineers use cofferdams too. Such vessels are too massive to be hauled ashore, and a cofferdam makes a perfect dry lock. The ship gets isolated from the water, and mechanics can repair it wherever it sits. Also, when a cruise ship needs to be expanded, engineers construct a cofferdam around it. Then they pump out all the water from the inside, creating a dry working place. The ship gets cut into two parts, and the process of its lengthening begins. There are several main types of cofferdams: braced, cellular, rock-filled, or earthen. For each of them, engineers need to figure out the best depth at which the wall should be put into the ground. It depends on the type of soil and the water reservoir itself. Braced cofferdams are mostly used during shallow water construction. Such a structure is actually a wall of sheet piles. Those are parts with interlocking edges. Usually, they're made of steel, but the material can also be reinforced concrete or timber. Sheet piles create something like a box around the needed area. Cellular cofferdams are also made of sheet piles, but in this case, the piles have a special shape. After being connected, they form cells that get filled with soil or clay. The cells, in turn, create a watertight wall. Thanks to its structure, it's exceptionally stable. Rock-filled cofferdams are used when there's a lot of rock at the construction site. They're built over the soil. This prevents the water from seeping into the cofferdam, and the rocks serve as reinforcement. Earthen cofferdams are built in areas where the water is less than 10 feet deep. They're created from the materials that are at hand: clay, sand, and even soil. There are also single-walled and double-walled cofferdams. The first type is used when the area of the construction isn't large and the depth is more than 20 feet. Such cofferdams are typically necessary for building bridges. Timber or wooden sheets are put into the sea or riverbed. After that, iron or steel sheets are added on the inside. On both sides of the wall, workers place half-filled bags of sand. Finally, the water gets pumped out and the cofferdam is ready for use. The double-walled cofferdam is used for large construction areas and when the water is very deep. Such construction sites need more powerful supports. This stronger cofferdam has two walls, which provides it with extra stability. Two piles get pushed into the waterbed with some space in between. The deeper it is, the bigger the space between the walls. Then they get attached to each other. After that, this space gets filled with soil. Cofferdams aren't cheap. This means that if one is used for a project, there are no other available options. For example, it's the best way to construct permanent dams. When the Hoover Dam was built, several cofferdams were put up to divert the water from the Colorado River. As soon as the project is finished, the water is pumped back into the cofferdam, and its walls, whatever they are, get removed. One more way of underwater construction is caissons. They're watertight structures that are put into the water. Even open, they remain dry inside. Workers can keep digging down until they reach some solid surface. That's where the caisson will be placed upon. What's so different about caissons is that they eventually become parts of the foundation for, let's say, a bridge or a dam. And even though you might not think of a bridge or a dam as an underwater construction, most of their crucial elements are underwater. For example, a large bridge wouldn't be able to hold its weight without massive supporting towers, and they stand in the water. There are several types of caissons: open, pneumatic, and box. Open caissons have no bottom. They're actually just vertical walls that allow builders to dig at the bottom of them. Pneumatic caissons keep the water from seeping through by using compressed air. This helps to maintain equal pressure inside and outside the construction. When workers dig out some materials, these get sent up through a special muck tube. When the caisson reaches the bedrock, workers fill it with concrete. Unlike others, a box caisson has a floor, and workers lower it onto a foundation that is constructed in advance. During the construction of the Brooklyn Bridge, engineers used two massive caissons. Thanks to them, they reached the bedrock and created the foundation for the towers of the bridge. And then there's also off-site construction. That's when things are not only built, but also assembled away from the site. In this case, engineers often use modular construction. That's when factory-produced building units are delivered to the site. There, they get assembled, like a giant Lego set. Structures are then usually floated to the site on huge barges, or they get towed there. After that, they're lowered in place. Some sink under their own weight. Others can only reach the seafloor after getting loaded with additional weights. This method of construction is rather expensive, and still, it's much more cost-effective than building right underwater. The latter needs skilled engineers and unique tools, and don't forget about the risks. But what about underwater tunnels? How on earth are they constructed? Modern tunnels are usually built with the help of massive tunnel boring machines. They even have a nickname: moles. Even though such a mechanism has an exorbitant price, several $1 million, it needs little time to create a long tunnel. The machine moves forward very slowly. It has a special circular plate with rotating disc cutters. They can easily chew through solid rock. The rock is then dropped onto an outboard conveyor belt. Another mechanism uses this rock to construct the tunnel's lining in the mole's wake. This way, the mole not only excavates the tunnel, but also reinforces the walls that will later support it. This method, and 11 huge tunnel boring machines, was used to build the 32-mile-long Channel Tunnel, and the whole process took only 3 years. Cut and cover is another method of creating a tunnel underwater. First, workers dig a trench in the ocean floor or riverbed. Then, they put concrete or steel tubes there, made in advance. After the tubes get covered with a thick layer of rock, the sections are connected. All workers have to do is pump out the water. That's how the Ted Williams Tunnel, connecting Logan Airport with South Boston, was built. There, they used 12 enormous steel tubes, more than 300 feet each, and the tubes contained already fully constructed roads. This is the Burj Khalifa. It's the tallest building in the world. It has 163 floors, and it's twice as tall as the Empire State Building, and 3 times taller than the Eiffel Tower. The total weight of the concrete for the building's foundation is 110,000 tons. That's like 2,200 Boeing 737s, or 50,000 SUVs, or 69,000 hippos. It took 22 million human hours to build. That means that if you were to build Burj Khalifa by yourself, it would take you about 2,500 years to do it. And now, imagine that huge thing slowly sinking into the sand until even its spire is underground. Skyscrapers are usually built on solid ground. Take a skyscraper in New York and dig a little deeper under it. There's always some kind of rock foundation to support the weight of the building. But if you dig a hole in Dubai, you'll only find sand. In theory, the whole city should have sunk in the sand, but it's still there. The main reason the Burj Khalifa stands firm is that the sand for the building's foundation was brought from Australia. Wait, but Dubai is built in a desert. There are billions of tons of sand there. Well, that's right, but the problem is its shape. There are lots of dust storms there. The wind picks up sand grains. They rub against one another, get polished, and gradually turn into microscopic balls. This makes the sand doughy, almost like snow. And if you squeeze a handful of such sand, there will be a lot of air between these balls. That's because they don't cling to one another tightly. But usually, sand grains are shaped like diamonds. If you squeeze such sand in your hand, the grains will press against one another like puzzle pieces. This way, they can withstand intense pressure. So, engineers imported millions of tons of sand to Dubai to create a strong base for the foundation of the building. The second thing about this type of sand is friction. The less smooth it is, the harder it is for you to slide on it. The building will literally cling to the sand with its foundation. Now, let's sneak a peek underneath the Burj Khalifa. First, the engineers drilled 192 holes, each about 164 feet deep. That's 3 times the length of a New York City subway car. Then, these holes were filled with concrete and about 39,000 tons of steel rebars to reinforce the structure. These are called piles. Concrete resists compression well enough, but it doesn't fare well when it gets twisted or bent. Luckily, steel rebars are great at dampening those forces. The sand around the piles is tight against the concrete. The friction between the sand and the piles keeps them from falling deeper. It's like sticking your hand in the sand at the beach. It can easily go down a dozen inches, but then the friction will stop it. When the piles were ready, it was time to create the base of the building, something like a concrete pillow. It's shaped like a flower with 3 petals, but this is not only for beauty, it's also for reliability. When you step on doughy snow with your feet, you fall all the way down to more solid ground. But if you wear snowshoes, you can walk on the snow surface. This is because your weight is distributed over the snowshoe area. The shape of the base of the Burj Khalifa has the same function. It distributes the construction's weight evenly, so that the building doesn't sink into the sand. When the base was ready, workers began constructing the building itself. Whoa, it really swings a bit. Don't worry, it's done on purpose so that the skyscraper doesn't collapse. If you make the construction too stiff and don't let it swing, at one point, a strong gust of wind can just break it at the very base, and it will fall. So all skyscrapers are made a bit flexible. When the wind blows, the skyscraper tilts a little. This puts a lot of force on one side of the building's foundation, but concrete tends to shrink slightly, which dampens that force. Then the concrete decompresses and returns back to normal. When the wind is especially strong, the spire of the Burj Khalifa can sway 6.5 feet. The architects have come up with an even crazier idea for Dubai: a spinning building. It'll be an ordinary skyscraper, but each floor will rotate 360 degrees. Engineers are planning to install a rigid rod inside the skyscraper. It'll hold the entire weight of the construction on itself. Then each floor of the building will be attached to that rod, and the inhabitants of each floor will be able to choose the direction and speed of rotation. So, building on sand is actually quite reliable and simple. It was much harder to build skyscrapers in Manhattan. There's hard rock that can support a skyscraper there, but it lies 10 stories deep underground. So, engineers came up with a solution. These are wells. First, a concrete ring is placed on the ground. Workers start digging a hole right underneath it. They remove soft soil, and the concrete ring begins to sink under its own weight. The builders then put another ring on top of it and continue digging. One by one, the rings go lower and lower. A small crane helps to lift the soil to the surface. It's essentially a vertical tunnel that leads to nowhere. When the well reaches the rock hidden underneath the soil, the builders climb back to the top. The well is then filled with concrete. It looks like a giant pile. A dozen of these powerful piles can support a large skyscraper. But it's much harder to create a building foundation in a seismically active zone. That means a place where earthquakes frequently happen. The method of protection against them is simple. Like with high winds, you need to make the building flexible. Let's look at the foundation of such a construction. Good old piles hold the enormous weight of the skyscraper, but the concrete pad of the building itself stands on huge springs. During an earthquake, the ground shakes and moves from side to side, but the springs dampen and compensate for the movement, so the building stays in place. Also, engineers surround buildings in earthquake zones with concrete circles underground. So, here's a skyscraper with its foundation. Here's one ring around it, and here's another. When an earthquake hits and the ground starts to shake, these rings dampen the force of the earthquake. And if around the rings it feels like strong waves, inside the perimeter, it's like a calm bay. Another option is to reinforce the building with steel beams. You may have seen these things on bridge piers, but in this case, there are small cylinders on each beam. Each cylinder is filled with oil and has a piston. When the building starts to swing during an earthquake, the piston starts to compress the oil in the cylinder. The oil turns the mechanical energy from the swinging into heat. This dampens the energy released by the earthquake. And sometimes, engineers have to construct a building in a place where there's a lot of water in the soil. If you drill a hole for a pile there and fill it with concrete, the water will wash out the cement or keep it from drying out. In such cases, you have to freeze that water. To do it, builders make a lot of small drill holes at the construction site. Then they put pipes into these holes and create a connected pipe system. There's a similar pipe system in your fridge. It's hidden under the inner paneling. Now, we pump some liquid nitrogen inside. The water gives off its heat to the liquid nitrogen and starts to freeze. Meanwhile, the workers have time to fill the pile holes with concrete. But water in its ice form takes up more space than in liquid form. So when the ice melts, the ground sags a little. So what if you want to build a city on water, like Venice? Then you'll need long piles. The builders of Venice used wooden ones. They had to get to the bottom of the lagoon first, and then they moved a few more dozen feet deeper through the soft clay soil until they reached the hard rock. The builders drove such piles around the perimeter of the future building, and the construction itself was built in such a way that most of its weight rested on the outer walls. If you dive underwater in Venice, you'll see hundreds of thousands of such piles. The task is more difficult if you build a bridge. In addition to a solid foundation, you have to take into account thermal expansion. The rule is simple. When something gets hot, it expands, and when it cools, it shrinks. Look at railroads. There is a gap between each rail. The clatter of the wheels you hear when on a train is born exactly on these gaps. When the sun heats the rails in the summer, they extend. This creates tension inside the metal. Then the rail can bend sideways or even upward, like a worm. But if engineers have provided such gaps, the metal will expand and fill that space. A bridge is exactly the same as a huge rail, and in hot weather, it can expand too. So engineers leave gaps there on purpose. You can see them on the surface of the bridge. They're usually covered with a sheet of metal that looks like a comb. When the bridge heats up, these combs come together. On October 30th, 1759, the inhabitants of the Middle East were jolted awake by an earthquake. Cracks appeared in the walls of their homes. Roofs began to crumble. People ran out of their homes and gathered in open areas. But because of strong shocks, they kept losing their footing and falling. A month later, there was another earthquake, but it turned out to be even stronger. Trees broke, houses collapsed, deep cracks appeared in the ground. The disaster lasted for 2 minutes. Oases, roads, and cities were destroyed. Incredibly, Baalbek's ancient buildings withstood earthquakes. Some historians state that this majestic and mysterious place was built during the Roman Empire, but many researchers disagree. Whatever the truth is, the city is one of the main archaeological phenomena of humankind. The most amazing building of Baalbek is the Temple of Jupiter. The inhabitants of the Roman Empire believed that Jupiter held power over lightning and thunder. The building looked like a platform with 54 columns. A massive roof rested on these columns. Today, you can only see 6 70-foot-high columns. Each of them consists of 3 sections and resembles a pencil. The cores of these pencils were made of lead. This made the columns exceptionally strong. Each of these pieces of stone weighed an incredible 80 tons. That's the weight of 35 Ford Explorer SUVs. Look, this is the largest block in the Great Pyramid of Giza. But compared to the blocks from Baalbek, it doesn't even look that impressive. The foundation under the Temple of Jupiter was preserved. That's how specialists figured out it consisted of about 25 monolithic stones, weighing 450 tons each. It means that the blocks from Baalbek weigh almost 4 times more than the blocks from Egypt. There are 3 more enormous limestone blocks in the foundation. They weigh 800 tons each. This is more than twice the weight of a Boeing 747 plane. Ancient builders must have had a hard time carving such giants from a piece of stone. And after that, they also had to pull them to the construction site and lift them to a significant height. Repeating these logistics would probably turn out to be a nightmare for present-day builders. To do this amount of work, they would need modern equipment. But Baalbek's constructors didn't have trucks, cranes with circular saws, or electricity. How did the builders of the past manage to do this? Scientists have a theory that includes ropes, winches, and lever systems. Naturally, the engineers of the past made all the gadgets from wood. Around 3,000 feet away from the ruins of the temple complex, there's a quarry. Archaeologists suppose that's where the stones for the construction were cut. They found a block of limestone there. It seemed to be too large even for this incredible place. The monolith got called the Stone of the South. It was 65 feet long and 13 feet wide. The ancient builders didn't have time to completely separate it from its mother rock. A group of scientists from Austria estimated that this piece of limestone weighed more than 1,000 tons. That's like 3 Boeing aircraft or 160 African elephants. There was another surprise awaiting the archaeologists near the Stone of the South. It was the second monolith that weighed more than 1,200 tons. But the ancient builders didn't stop at that. They continued to work. In 2014, in the same quarry, German archaeologists unearthed a block that weighed 1,650 tons. No one has figured out yet why people of the past needed a piece of stone that weighed as much as 125 school buses. It's also unclear how they were going to move this giant and why they didn't finish the job. In any case, this third monolith is the largest processed piece of stone in human history. There are more questions than answers. Some researchers believe that people of the past had high-tech equipment. Others don't think so, but are eager to understand how the builders managed to move those stones. There's a huge number of ancient buildings and artifacts on the planet. Lots of them make researchers scratch their heads. Near the Pyramid of Djoser in Egypt, archaeologists have found a network of tunnels. This place is called Serapeum. It contains 24 sarcophagi weighing from 70 to 100 tons. The giant boxes are carved from a single piece of granite and covered with heavy lids. The sarcophagi are perfectly symmetrical. To the touch, their walls are as smooth as glass. Even with the current level of technology, this is very difficult to do. But the ancient Egyptians managed this feat. The Lycurgus cup is a priceless artifact and example of ancient nanotechnology. It's made of glass that can change its color. If you put a source of light in front of the cup, it turns green. If the light is behind the goblet, it becomes deep red. In this case, the figure of Greek king Lycurgus turns pale purple. Scientists understood how this color change worked only at the end of the 20th century. Through microscopes, they saw nanoparticles of silver, gold, and copper. They had been added to the glass matrix. Thanks to this, you can observe a color change called dichroism. Interestingly, the gold and silver were grounded into a fine dust. It's almost impossible to do this by accident. Most likely, the ancient experts knew for sure what they were doing. Bolivia has a curious place called Puma Punku. It looks as if an ancient giant played there with an enormous construction set. And after the game, they forgot to put the pieces back into the box. But there are no giants, and the huge stone blocks were carved by ancient builders over 1,500 years ago. Some of the rocks weigh 100 tons. The blocks were brought to an altitude of almost 13,000 feet above sea level from the quarry 60 miles away from the construction site. There's no forest in that area. This means the builders couldn't use trees to make wooden rollers. The monument belongs to the Inca civilization. Scientists are sure they didn't know anything about wheels. In 1992, the inhabitants of a Chinese village decided to drain a pond. Their ancestors had been using it to wash clothes and catch fish for hundreds of years. They kept pumping the water out for 17 days. At the bottom of the reservoir, they made an unexpected discovery. The villagers saw an entrance to a cave going down to a depth of 100 feet. The incredible find was named the Longyu Caves. Unknown builders carved out 320,000 square feet of galleries. There are separate rooms, bridges, pools, and columns that support the ceiling. The walls of the cave are covered with strange carved lines and patterns. Scientists haven't found any information about who built the caves and why they did it. The construction technology also remains a mystery. Antonio Stradivari lived in Italy in the 18th century. He created musical instruments. More than 600 of his works have survived to this day. 500 of them are violins. One of the instruments was sold at auction for $16 million. The violins made by this master sound clear and deep. Researchers can't understand why Stradivarius instruments produce such unique sounds. Perhaps it's all about the varnish the master used to cover the violins. The answer may also lie in the wood the instruments are made of. In those days, Europe had a cold climate. Because of this, the wood became denser, and the instruments made of it sounded especially pleasing to the ear. In the Indian city of Delhi, there's a 23-foot-high pole. It weighs 6.5 tons and is made of 98% wrought iron. The 1,600-year-old pillar has no signs of rust or decay. Scientists believe that the monument is so well preserved thanks to the dry weather and the chemical composition of the metal. It might be resistant to corrosion. And still, researchers don't know how the blacksmiths managed to make an iron pillar that's not afraid of rust. It seems like a tough feat, even for modern metallurgists. The Al-Nasla rock is divided into two parts by a perfectly straight slit. Each boulder stands on a small pedestal. Some people believe this is the evidence of ancient laser technology. But geologists think the split happened due to the ground shifting or natural vibrations that occurred under the rock. This process led to the appearance of the crack. It had been deepening for thousands of years, and gradually, the natural monument took the form you can see today. Fire! Fire! Everyone gets out of bed and rushes out to the street, but the whole city is ablaze. It's 1871, and the Great Fire of Chicago has just started. For 2 whole days, the Windy City, including the business district, saw nothing but ash, smoke, and flames. The fire stretched out for 4 miles, causing around $200 million in destruction. No one really knows how the Great Fire started, but some theories include a cow kicking over a lantern in a barn that quickly spread to the city. Other theories include a typical human mistake, and even a meteor shooting down from the sky, starting the massive fires. The problem was that any metropolitan area during the late 19th century was made almost entirely out of wood. Throughout history, our ancestors used wood to build shelters, ships, carts, and everyday objects, since wood was literally all over the place. Everything from cooking utensils, wheels, and tools to furniture was all wooden. Walking around town back then wouldn't feel as congested as a typical urban city today. After the Great Fire, buildings became predominantly made out of steel and concrete. China has the oldest and tallest timber building, or a skyscraper. It was built almost 1,000 years ago and is 220 feet tall, which is the equivalent of a 23-story building. It's still standing today after being restored a bunch of times. It survived around 7 major earthquakes. But just because a structure like this is still standing tall today, it doesn't mean we can go around building wooden skyscrapers out of nowhere. A lot of tall wooden structures exist today in Europe and the US, even though they were built after the steel and concrete rise. But they're just between 8 to 13 stories high, not enough to be labeled as skyscrapers. Japan plans to build a wooden skyscraper more than 1,100 feet tall, dubbed as the W350 project. They're scheduled to complete it by 2041 and turn modern cities into wooden wonderlands. The building will be made of 90% processed wood and 10% steel, and it won't be made out of regular wood. They'll use cross-laminated timber, or CLT, which is many sheets of wood glued and stuck together, creating a large plank that is even tougher than steel. But wooden structures are vulnerable to fire. Back at the time of the Great Fire of Chicago, They didn't have fireproof coatings that could be applied on the beams. Even steel structures have such coatings. And the beams of today won't be like the ones in the past. They're sturdy and big, so big that extremely high temperatures can't set them on fire. And in the case of steel, these boiling temperatures that can burn the wooden beams with the fireproof coatings will simply melt the steel structures. So either way, the problem of fire is unavoidable, and the aftermath is still the same, be it wood or steel. Every tall building sways with powerful wind. Wooden skyscrapers are no exception, and might be in more critical danger than their steel counterpart. But some engineers designed a way to avoid this problem by constructing the wooden building out of diamond and triangle shapes. A triangle by nature can have a secured base better than a rectangle. So by creating a triangle base, which would be the bottom third of the building, a wooden skyscraper can resist external forces like the wind. Plus, with such large real estate in the bottom, there would be enough place to build additional housing units or shops near the ground. Building a wooden skyscraper won't necessarily be on site. Engineers and architects will create the planning and blueprints on computers to guarantee the best possible design and structure to ensure aesthetic appearance and sturdiness. Workers can build the standardized models at a nearby factory and transport the prefabricated structures to the site. This system will save more time and have quality control from the ground up. In a concrete building, the cement has to be poured into empty beams and shapes that have to dry in days or weeks. Steel needs to be melted and molded into shapes to fit the structure and design. In the factories, the cross-laminated timber can be cut automatically and supervised by people to make sure nothing goes wrong. This will eventually save costs by not having that many construction workers. And when it's time for building, all they have to do is bring the structure in pieces, put them together, and raise it up. It won't be as messy as a regular construction site and won't take too much time. Only fixing the electrical planning, plumbing, and other internal operations will need a lot of on-site work. Then, a team for the finishing touch will come and do some last-minute brush-ups to make sure everything functions properly. And then, voila! You've got yourself a wooden skyscraper. Wood, in general, is more flexible and lighter than concrete and steel. A wooden skyscraper would withstand an earthquake better than a concrete building and would be less likely to collapse. And since wood is a natural insulator, residents can save on heating and cooling costs. Steel and concrete don't grow on trees, but wood does. And don't worry, it won't even make a dent as far as deforestation. People use less than 1% of the world's woods. Engineers and architects will have special timber farms grown for the purpose of construction. But if the world decided to turn to wood for the buildings of tomorrow, then mass deforestation would lead to extreme disasters in our forests. According to some researchers, replacing steel with wood could impact around 40% of forests annually. That still won't compensate for the new wood grown each year. Having wooden buildings around will help with carbon benefits. It requires less energy to produce than steel and concrete. According to some studies, a large building made of wood will have a much smaller carbon footprint than one made of steel and concrete, which amount to around 16% of global emissions. And since wood is lighter than steel, it'll save on fuel costs and require less to transport it, which will reduce emissions even more. Something like this will take decades to plan out and execute if people really wanted to make the switch. When people started switching to steel buildings, everyone started to notice its benefits. In the long run, wood rots and absorbs and releases moisture, which can compromise a structure. Some people have chosen recycled plastic to build new homes by turning it into rough powder and shaping it into whatever is desired. They created beams, blocks, bricks, and pillars. In South America, a group of people are already doing this by creating small two-bedroom houses made mostly out of recycled plastic. It's cheaper to make, gets rid of waste, and only takes 5 days to build, with 4 people building it. Maybe one day we'll see skyscrapers made out of recycled trash, and maybe even whole cities made out of trash. In Yemen, there's a small city known as the world's oldest metropolis. In the middle of the desert, the locals had to find a way to shelter themselves without the abundance of trees. Shibam, aka the Manhattan of the desert, is made out of fertile soil, hay, and water that were made into bricks and left to bake under the sun for days. This city was a pit stop for many travelers arriving in caravans back in the day. Most of the buildings were 7 stories high, and the ground floors were used to keep livestock and crops. The upper levels were places for socializing and looking out for any newcomers. Mud buildings are natural coolers. The mud repels heat, leaving the cool atmosphere trapped inside. The first reinforced concrete skyscraper was built in Cincinnati, Ohio in 1903. It was 16 stories high and wasn't even expected to last the whole night. People thought it would crumble from its own weight, while others believed it would topple over. When they removed the support columns, a local reporter stayed awake all night to document the building collapsing. But they were all wrong.